Great. Thank you very much to the organizers for organizing the meeting and for giving me the opportunity to speak here about few-body physics. And I would like to start off by thanking the people who've done the work in my group, in particular postdoc Qingzi Guan and former student Yanqiang Yan. So if we think about cold atomic gases, we might ask, why do we care about few-body physics? And I just put up two equations here, one for bosons and one for fermions. This is the Gross-Petchevsky equation here that many of you have seen. It's a mean field equation, so it's sort of the interaction that a single particle feels as it moves in the background. And the interaction is given, or sort of the interaction strength between the single boson and the background is given by the S-wave scattering length, which is a two-body quantity. And similarly, if we think about a two-component Fermi gas, here I've written down the microscopic Hamiltonian, then the interaction between the two spin components, between, say, an atom from up and an atom from the down component, is again given by the two-body S-wave scattering lengths, and here I've just used contact interactions. And this two-body S-wave scattering lengths can be obtained from measurements experimentally, and this is just one example for such a cross-section measurement. Now you might say, well, you said you're going to talk about few-body physics. This is just two-body physics. Few particles requires at least 3 particles. Well, we can talk about that as well. In the top here, I have a Fermi gas. These are pictures from Debbie Jin's group. And what you see is that the Fermi gas, the two-component Fermi gas, as we go to the infinitely strongly interacting regime, is actually stable. This was a big surprise when it was sort of a big question posed, among others, by George Birch from the nuclear physics community. And it turns out that this system is actually stable. And the underlying physics is really few-body physics. The fermionic system does not actually support a weakly bound 3-body state. On the other hand, if you go to bosons, the 3-body recombination rate scales as the scattering length, this 2-body quantity, to the power of 4. So if you do go to unitarity, so you do go to a large scattering length, what you expect is you expect large losses, and that's why it's hard to really study the unitary Bose gas, as was already mentioned by Zoran a couple of days ago. On top of this AS to the 4 scaling, you do see substructure here, and this substructure is a signature of Efimov physics, of the Efimov effect, which is really something that's due to Vitaly Efimov. Again, it's coming to us from the nuclear physics community. It was proposed originally in the context of the triton and also carbon. And the fact that it's coming to us from sort of the triton also already hints at the possibility that these few-body processes that we can now study in ultra-cold gases have a much broader impact beyond cold atom physics. Namely, they may help us to eventually understand the nuclear chart better, at least of the very weakly bound nuclei. So this is sort of the essence of the Efimov effect here. Here I'm plotting the three-body energy. These are the red curves here as a function of 1 over the S-wave scattering length. This is our 2-body quantity that characterizes the 2-body interactions. And what's really amazing about this 3-body spectrum is that it's entirely determined by this 3-body parameter. So we have the energy here. We have 1 over the S-wave scattering length here. And knowing one of these curves, which is determined by this 3-body parameter, we immediately know the shape and where the other energy levels of the 3-body systems lie. And this is really due to Efimov's radial scaling law. And one way to sort of see what this implies is that if I take 2 neighboring energy levels and I do the scaling as prescribed by Efimov's radial scaling law, we see that the two neighboring energy levels actually collapse. And this really highlights that there's a discrete symmetry, discrete scaling symmetry in the three-body system, which for identical bosons, that scaling factor is 22.7. You might say, well, this is nice. Can we observe this? And yes, this has been observed by really beautiful work in Rudy Grimm's group. These are two plots where we're seeing the three-body recombination as a function of 1 over the scattering lengths. These are loss features, which are due to the fact that the three-body energy is actually resonant with the three-atom continuum. And what we see is we see enhanced losses at this point here and at this point. So we see enhanced losses here at this scattering length and at this scattering length. And according to Efimov's zero-range theory, these two enhanced loss features should be spaced by a factor of 22.7. And from the experiment, one gets 21.6, which is really a nice confirmation of the zero-range theory. So we can also look at a complementary experiment. This is a helium molecular beam experiment where I was involved in the theory. This is sort of, according to John Doyle, a good old experiment. We have a molecular beam coming in from the right here. It goes through a grating. That grading allows one to basically do a mass selection, isolate the trimer portion of the beam. And now what's unique in this experiment is that there's actually an intense laser coming in that's ionizing the atoms of the helium trimer. And this really allows one, via the Coulomb explosion approach, to image the quantum mechanical density of Efimov states. And this is shown here. On the left, I have the excited state as calculated by theory. This helium Efimov trimer is really, this is the excited state. It's been predicted to be an Efimov state since the early 70s. On the left here, we have the theory. In the middle, we have the experiment. This is really a quantum mechanical density of an Efimov state here. What you might not be able to see is this excited state is actually about 8 times larger than the ground state, which is shown on the right here. And this is, again, can be explained by Efimov's zero-range theory. And the other thing that you can see here is that there's really a distinct difference between the helium trimer ground state, which is not an Efimov state. If we look at this normalized density plot here, you see a distinct difference between the ground state and the excited state, this Efimov trimer, which really has sort of like a diatomic molecule plus dangled on single atom structure. So what I like to do in the following is I like to discuss the extensions of the Efimov effect to more particles. There's been a lot of work on thinking about how does this sort of three-body physics extend to 4, 5, 6, maybe even 30 particles in the equal mass case. What I like to tell you about today is just the four-body sector, maybe looking a little bit at larger systems, but in the case where we do have an impurity. And then I like to connect this with work done by other groups, and in particular, how does the Efimov physics really interplay with, say, Polaron physics? And in the last part of my talk, I like to go back to the three-body system with equal masses, 3 identical bosons, and sort of ask whether the Efimov scenario, this discrete scaling symmetry that underlies the Efimov effect, if this really survives if we add other two or single body forces to the system. This was discussed previously in the context of a two-body dipole-dipole interaction in Green's group, and I'll be telling you about what happens when we add single particle spin-orbit coupling terms to the system. But let me start off with the Efimov scenario for more particles. And to set the stage, I'll show you the sort of scenario for 4 identical bosons. So again, this is energy here as a function of 1 over the scattering lengths. The green curves our 3-body Efimov trimers. And what's been found is that there's 2 4-body states that are attached to each of the Efimov trimers. And the 4-body states are connecting, running into the 4-atom continuum on the negative scattering length side, and run into the dimer-dimer continuum on the positive scattering length side. So that's where these states cease to exist. So the question is now, what happens if we don't look at the 4 identical boson case, but we replace one of the bosons by an impurity that has a different mass? And in particular, I like to look at a situation where we have a mass imbalance. There are nice experiments on cesium-lithium systems where the scaling factor lambda is not 22.7 as in the identical boson case, but 4.87. And a smaller scaling factor basically means that it's a bit easier for the experiments to access the regime, to access multiple resonances. So you don't need such a big dynamical range if you want. The theoretical challenge in treating these systems is that we really want the trimer size to be much larger than the range of the interactions. So ideally, we would like to have 0 range interactions between the bosons and the impurity, but this is for technical reasons not possible. So we work with finite range interactions. And so we need to make sure that our trimers and tetramers are large compared to the underlying range so that we're in the universal regime. And we've considered 2 approaches. One is we look at resonance states. This means we look at 4-body states that are attached to excited 3-body states. This is very much like in the cold atom experiments, but it's theoretically more challenging to calculate resonances than bound states. And the other approach is a little bit more artificial, where we add a repulsive 3-body potential. It's sort of an ad hoc 3-body potential that basically pushes the atoms out and allows us to look at bound states as opposed to resonance states. And here are the results from these 2 approaches. For the first approach, we only looked at the positive scattering length side. For the second approach, we have the energies as a function of 1 over the scattering lengths for both positive and negative scattering lengths. So what you see is that we again have 2 4-body states that are tied to the Efimov trimer state. If we look at where the 4-body states hit the 4-atom continuum, so this is a prediction for where one should see enhanced losses, what we see is that the 2 approaches give relatively compatible results and predictions. So this is telling us that we are reasonably well in the universal regime. And our hope, of course, is that this is now going to be observed in the cesium-lithium system. There are 2 groups, the Heidelberg group and the Chicago group, who've already seen 3 consecutive 3-atom features. But there have not yet been unambiguous signatures of these 4-body, 4-atom resonances that we're predicting, although there have been hints that there might be something. And Matthias Weidemüller's group is sort of building up to possibly improve the experiment. So now we can ask the question, okay, we have these 3-body states, 4-body Efimov states, maybe even larger systems. How does this fit into sort of the bigger atomic gas? So what happens if we look at placing a 3-body trimer, Efimov trimer, 4-body state into the background? And this I'd like to discuss in the context of the equal mass system. So I'm still considering an impurity, a red impurity, but now the impurity has the same mass as the surrounding blue bosons. And this is sort of our generic Polaron picture here. We have the impurity. We have this infinitely strong interaction between the bosons and the impurity. And for equal masses, we know that there's a 4-body state that's universally tied to the 3-body state. And there's supposed to be also an excited 4-body state. Moreover, we know that there exists a 5-body state that's been calculated by Pardena-Ardila and co-workers. And what they predicted is that there should not exist a 6-body state. We do have some preliminary evidence that the 6-body state exists. So if we go to this very low density setting, then you might expect that at extremely low density, where the bosons are far away from sort of this cluster state, that you approach a regime where you either form a 5-body cluster, or maybe a 6-body Efimov cluster, or maybe there exist larger clusters as well. But it's also clear that this picture has to break down at some point, because if you go to high density, then your sort of few-body states that you started off with are going to be disturbed significantly. So you should not be able to sort of just think of an Efimov trimer here. There should be a lot of disturbance. And so it's really an interesting question, what happens sort of in this intermediate density regime. So on the left here, this is a figure taken from Yoshida's paper. On the left here, we have this low-density regime, and within their approximations, they recover the trimer. If they improve their variation of wave function a little bit, they get a tetramer. We might expect that there should be a pentamer here, maybe a sextamer. But then in this intermediate density regime, there's a question as to whether this is really universal, whether the physics is really governed by Efimov physics, as has been predicted in this paper, that makes a nice connection between few-body physics and the Polaron physics. And just as a reference point, the Aarhus experiment, which uses potassium in 2 different spin states, works at about this regime in this intermediate density regime, where n to the 1/3 times the 3-body parameter is 10 to the 2. So I think there's a lot of interesting physics to be done in connecting the few-body physics with the many-body physics. So now I'd like to tell you a little bit about sort of going back to the 3 identical boson systems. What happens to the Efimov effect as we add spin-orbit coupling to the system? And as I mentioned already, the Efimov effect is tightly linked to a discrete scaling symmetry. And to discuss this a little more, let's start off with a little warm-up problem, just a 2-body system. I've just written down the Schrödinger equation and the relative coordinate here. And let's discuss the continuous symmetry in the 2-body system with zero-range interactions, just to sort of bring the concept across. So this is our Schrödinger equation. If I now continuously scale, so I just introduce the scaling lambda squared here for the time, the scaling of the length by lambda, scaling of the energy by lambda to the -2, and I plug this into the Schrödinger equation, then it's very easy to see that the Schrödinger equation does not change under this under these scaling transformations. So we have a continuous symmetry in this zero-range Hamiltonian. Now, if we go to the identical boson case, where we have point-like contact interactions here for each pair, and I've also introduced a contact 3-body interaction here, then what you see is that you can also introduce this scaling transformation, where we now scale time, we scale position, we scale energy, and we scale the strengths of the 3-body potential as well, where I've parameterized the strengths of the 3-body interaction by this kappa star, where kappa star is defined by the energy of the 3-body system at unitarity. Anyways, if you do the scaling transformation, you can convince yourself pretty quickly that the three-body Schrödinger equation also possesses a continuous scaling symmetry. What's not so obvious and what's really non-trivial is, and you can read about this in Bratton and co-workers' work, and of course this goes back to Efimov's original proposal. What's not so trivial to show is that the time-dependent Schrödinger equation for the three-boson system also possesses a discrete scaling symmetry. And this discrete scaling symmetry is just as before, with the exception that this three-body parameter, essentially the strength of this three-body potential, is not being changed. And that this lambda naught, the scaling factor, that's exactly this factor of 22.7 that I've told you about. So under this transformation, the energy spectrum does not change either. So the question is now whether this discrete scaling symmetry, and that is whether the Efimov effect, really survives if we add other forces to the problem. And what I would like to add to the problem is a 1D spin-orbit coupling. So here I've just written down the single particle Hamiltonian. So we have the normal kinetic energy. We now consider two hyperfine states that are coupled via these two-photon processes. So we have sort of a Dirac-like dispersion where we have this Raman coupling and the detuning here. The Raman coupling is going to open up a gap in the single particle dispersion curves. And if we have this additional single particle term in our Hamiltonian for each of the three bosons, I can write down the relative three-body Schrödinger equation. I've sort of sketched it here. We have kinetic energy, we have two-body interactions, we have the three-body potential again, but we also have the spin-orbit coupling term, the Raman coupling term, and the detuning term, which is actually a generalized detuning term that depends on the physical detuning as well as the center of mass momentum. And now you can convince yourself again very quickly that the system possesses a continuous scaling symmetry if you additionally scale the spin-orbit coupling strengths, so this guy here, the Raman coupling, as well as the detuning. So the question that we're asking is, does the system also possess a discrete scaling symmetry? And to check this, what we did is we performed calculations where we changed, for example, the scattering lengths, the spin-orbit coupling strengths, the Raman coupling strengths, and the detuning according to the prescriptions that are given to us by the radial scaling law, but we do not change the three-body parameter. And sort of the upshot from these calculations is that if you look at the three-body energy, say, for the ground state, you look at the three-body energy for the excited state, now for these scaled parameters, as one would expect for if the generalized radial scaling law would be valid, then what we find is that these three-body energies really collapse onto each other if we apply this generalized radial scaling law. And why do I use the term generalized radial scaling law? I use the term generalized radial scaling law because we now actually have 5 parameters in our space and not just 2. So here we have energy. We have 1 over the scattering lengths. That's what we had before. But we also have the strengths of the spin-orbit coupling, the Raman coupling strengths, and the generalized detuning. So this gives us a 5-parameter space. And we have checked that neighboring energy levels collapse as we apply the scaling to all 5 parameters. So why does this discrete scaling symmetry survive? Well, at this point, we don't have an analytical proof. We have numerical evidence. But in essence, the message is that the spin-orbit coupling terms are in the low energy sector, while the three-body parameter is set by high-energy physics. And so in the language of effective field theory, we have a scale separation, and this sort of protects the discrete scaling symmetry from being broken by the, or violated by the spin-orbit coupling terms. So I've told you a little bit about Efimov physics, which is really a very unique situation in the limit where we have strong interactions. We only have S-wave interactions. The scattering length is much larger than the effective range. I've shown you that the generalized Efimov scenario for the boson system with an impurity has similarities with the identical boson case. And I think there's a lot of interesting work to be done for larger systems and for Efimov states embedded into the background. I also told you about spin-orbit coupling and how that affects the three-boson spectrum. And the key thing is that the discrete scaling symmetry is preserved. However, we are now working in a 5-dimensional space and not in a 2-dimensional space. So as an outlook, sort of think there's really a lot of interesting things to be done here. So one of the things that I'm dreaming about is to really take the helium Efimov trimer and to watch it respond to a perturbation in real time and sort of look at wave packet dynamics. And to do this will really require to marry high intense laser physics with with cold atom physics. So the molecular beams have sort of a temperature around a Kelvin or so. And what we've looked at so far in the two-body sector really looks very, very promising. I also think that there's a lot of opportunities in the few-body sector to look at equilibration and thermalization with single-atom resolution. And I think we'll hear more about sort of these optical tweezer experiments at this conference. I think there's a lot of opportunity here for few-body physics. There's a lot of interest in effective few-body interactions. This was originally done experimentally in Emmanuel Bloch's group. There's now beautiful work by Junier's group. And that's sort of connecting few-body physics with applying it using clock transitions and really getting in very, very precise measurements. And lastly, I like to point out that there's also very interesting few-body physics if you go to the lattice systems. You can really look at Magnon's spin excitations on a lattice and look at bound states, three-body states there. So with this, I'd like to thank you for your attention.